Hello and welcome to the Porch Privateers technical overview. We're excited to share our progress and the insights that we've gained working on the project over the last few months. So without further ado, let's take a look at what we'll be going over today's presentation. So we'll start with a high-level overview of the problem and our solution, and then show you what our architecture looks like to help solve the problem. We'll then dive deep into each subcomponent of the architecture, which will be presented by each respective team member. With that, let's go right into our problem and solution. Currently, an estimated 36% of Americans have experienced package theft in cases where a delivery has been left unattended for long periods of time. This kind of criminal activity is very common since people often order valuable items online, especially around the holiday season. The Wichita Police Department is looking for a solution to deter local porch pirates, and the solution that we have developed is a palm-sized, portable, internet-connected device that can be affixed to or placed inside packages to detect any unexpected movement and wirelessly issue alerts to concerned parties. Our solution can be mapped out appropriately as shown in this diagram. Here, the node will consistently track its motion and use that data to alert authorities. The data is then relayed through the Wichita State University's network to a front-end application showing relevant authorities the status of the package. Let's take a closer look at how the node exactly determines its motion state and transmits the data in this next slide. As I previously mentioned, the node is affixed to a package and has the ability to tell when it is stable on the ground or picked up and in motion. When the device detects movement, it starts recording location data and proceeds to send an alert to an application notifying concerned parties of a possible theft in action. The node consists of a microcontroller, a 9 degrees of freedom accelerometer, a GPS module, and a LoRaWAN module allowing for wireless communication. The accelerometer senses motion roughly every 500 milliseconds or so, and collects this data momentarily to gauge if the package is being tampered with. If there is significant motion, the GPS module is activated to check if the package latitude and longitude coordinates are changing. Once the node detects the package location actively changing, it alerts the closest gateway through LoRaWAN. A string of information that includes a Unix timestamp, last recorded latitude and longitude, and acceleration on 3 axes is packaged into a compressed and AES-256 encrypted payload and is then transmitted through the RFM95 LoRaWAN chip. I'll now pass it on to Joseph to take us through exactly what happens to the data once it's received by the gateway.
Thanks, Abhishek. So in the future of our project, I'm going to be focusing more on these node to gateway interactions that I'm going to be deep diving into with you real quick. So what is the node to gateway interaction? What does that mean really? Essentially, once the device has detected motion, this step is how the device will be sending its message to the WSU network. This message will need to reach the end user eventually, but first it must go through a server, which Austin will be talking more about later, and that server will redirect information to the correct place. Before any of that happens though, the message will need to be received by a gateway that can then send that info to this aforementioned server. So specifically, this interaction between the node and the gateway is what I'll be focusing on. So how are we planning to carry out this step? Once the device or node decides to send a message through the RFM95 LoRaWAN chip, it will transmit that message out to be picked up by a LoRaWAN radio or gateway, which will be hosted by Wichita State's Information Technology Services. To find nearby gateways, we will need to register our device on the Things network, which is essentially a large network of LoRa-connected devices. Along with this network, we will also need to make use of the Radiohead library, which is a library for programming focused on messaging via radio on microprocessors such as our LoRaWAN node we're using. With this network, and through the use of the Radiohead library, we'll be able to find the MAC address of a nearby WSU ITS LoRaWAN gateway, so that then we can send our binary payload to it. The payload containing GPS data, acceleration data, and a timestamp will be received by a gateway or radio on WSU's network. After our payload reaches that gateway, it will next be sent using Ethernet and TCP/IP to a MQTT client running on the server to then be interpreted and rerouted to the appropriate parties. So what will be the output of this step? The gateway will receive a binary payload from the node and also output a binary payload to then be sent to the server. This payload still contains the latitude, longitude, time, and acceleration data as mentioned previously by Abhishek. Next, Austin will be going more in depth with the specifics of the server and networking next steps.
Thank you, Joseph. I will be responsible for the server implementation, which lives in GoCreate within the John Bardo Center on campus. The server has custom software and networking in which our team provides. All access to the network requires permission from WSU ITS and their VPN. Our method of data dissemination is Message Queuing Telemetry Transport, or MQTT for short. On the server, an MQTT broker offers an IoT service for publishing and subscribing data by topics. Topics can be consumed just like channels on TV or radio. A custom MQTT Go client running on the server will receive a binary payload on a specified port from the LoRaWAN gateway using Ethernet and TCP/IP. This client will decrypt the message using TLS and SSL while transmitting the payload to the MQTT broker with the posted topic. Any subscribers opting in for a posted topic will receive the data on a MQTT front-end client running on their phone or computer via TCP/IP. Next, Devin will walk us through how the data is visualized on the end node or end user devices.
Thanks, Austin. After we ingest the data in the last step, we need to organize and display it to the user. This is where our front-end application comes in. For receiving data, the application utilizes a lightweight MQTT client, which will be subscribed to our device communication topics from the MQTT server. Building our application on web technologies, we can be flexible in how we choose to deploy it. The application can be run either in a web browser or packaged for mobile platforms like Android and iOS. This is useful since officers will be able to monitor deployed devices, whether they're at the station or in the field. Our application will allow officers to view each device's motion and location data collected after alerts are sent out. They will be able to see the location of devices deployed in the field as pinpoints on a map. When the device begins sending alerts, location and package motion status will be updated in regular intervals. This will allow an officer to easily retrieve the device and catch the porch pirate in the act.
That brings us to the end of our presentation. We want to thank everyone who made this possible, specifically Professor Andy Stallard and Ron Augustine, along with the rest of the Wichita Police Department and Wichita State University team. We really appreciate you taking the time to listen to us today, and we hope to see you at the virtual open house. Thank you, and have a great day.